Dear friends, it's a great pleasure and honor to participate in your conference this year. In collaboration with the other partners of the outPHit project, I will present to you the methodology of streamlined renovation in residential buildings in Athens, Greece. First of all, some words about the project outPHit. Over the years, a wide variety of methods have been developed to make energy retrofits both faster and cheaper. outPHit is taking advantage of two main methods, in particular with the Energiesprong standard as the basis, the streamlined renovation and the prefabrication. Serial renovation and Energiesprong approaches make use of prefabricated components assembled off-site and transported to the construction site, while a streamlined approach helps building owners rank alternatives at each critical step in the process, building the case for investments in energy savings. For Greece, the second option is the interesting one for residential buildings. This is mainly because of the typology of the buildings. As you see, we have single or multi-family houses with heated basement detached or attached. We have single or multi-family houses with suspended floor detached or attached. And we have also historical residential or non-residential buildings where the facade cannot be modified. Please also think that all the buildings before 1980 in Greece are uninsulated, totally uninsulated. We know that there are things in deep energy retrofit which are easy and doable, like insulation or new windows or improving the air tightness or improving shading systems. But there are also others challenging, like the study and the energy balance simulation, the thermal bridges, and the planning of mechanical ventilation with heat recovery. The commonly renovation practices in Greece has to do with external insulation, placement of new windows, but without a good installation, a good thermal bridge for installation, and airtight tapes, installing of solar domestic hot water collectors on the roof, together with the boiler. We know also that deep renovation principles should also include mechanical ventilation with heat recovery, placement of proper windows with airtight tapes and non-metallic spacers. We must improve the airtightness of the building, and we must also solve and eliminate as much as possible the thermal bridges. Within the framework of the project, we studied 3 buildings in Athens, one single family house with a suspended floor, one other building with 3 apartments in Marousi, and we also made a case study of a multi-family house where we will renovate one single apartment. I will speak to you about the first one, the single family house, which has a treated floor area of almost 150 square meters, with a significant loss problem that the ground floor is suspended and an open unheated space, so there are significant losses which otherwise would be to the ground. The client wanted with the renovation to create 2 apartments, one small one with 2 rooms of 50 square meters and another bigger one with 100 square meters. The total renovation budget was 120,000 euros, which means about 130, less than 130 US dollars, including 24% VAT, which means taxes. So you see that 1/4 of the cost is taxes. This is something very high in Greece. The building information, we have to deal with a single family house of the 60s, which means totally uninsulated. We have replaced but cold aluminum windows. We have mold at the interior side of the surfaces of the building assemblies. The steps of the renovation of the energy efficiency of the building are about to be completed. We have already done the reparation of the building assemblies and the separation of the two dwelling units. We have replaced the old windows with new ones and with new blinds and with a thermal bridge-free installation. We have an airtight building, an airtight envelope. We will do now the blower door test. We have applied the exterior insulation, and we have also installed and functioned two HRV units. Briefly about the insulation, we use the EPS mainly, EPS materials, 10 centimeters for the external walls and the floor and the ground floor, 8 centimeters for the ground floor slab, and 20 centimeters, 10 plus 10, for the roof slab. For the airtightness, the main material is plaster in Greece. Thank God all buildings are plastered, so if you improve the plastering, then you have no problems with airtightness. For the windows, we use the 1.1 UF profile with and the glazing with 0.6 and 0.54 G value because of the bad orientation of the buildings. Of course, we used tapes for airtightness. The ventilation concept has to do with two units because of the two apartments. We have a big advantage in all the residential apartments in Greece. There is always, or almost always, a storage room above the main bathroom, as you see here, which is normally somewhere in the center of the house and in front of a corridor which drives to all rooms, and there you can put your ventilation units. On the small apartment, we decided to put the ventilation unit inside the wall, the external wall, in the area of the kitchen, and there it is very, very easy to go to the bathroom and to the other rooms. The challenges of the project, the most important thing in streamlined renovation is the detailed planning, in our opinion. For the Greek reality, this means mainly elimination of the thermal bridges in balconies and pillars and thermal bridge-free installation of windows. We have kilometers of balconies in every building, and this is a main problem. The challenge is to plan the best possible cost-benefit ratio in these procedures. For example, do we have to insulate the whole balcony, which is the optimal but expensive solution, or can we insulate just up to 1 meter in front of the wall and eliminate the risk of condensation and mold? Our models in several cases show that this is doable in the Greek climate, and so we can say that this is the cost-effective solution of minimizing balcony thermal bridges, and this with as little hassle as possible. Here you see the comparison of the energy demand before and after renovation. It is obvious that the efficiency factor is over 10, and this happens in every building in Greece which is built before 1980 because all these buildings are uninsulated. We choose to use the component method for certification because, as we said, we are searching for the cost optimum solution, and this is the cost optimum solution in these cases. You can understand that even with 35 kilowatt hours per square meter for heating or 17 for cooling, we are still in a very good, really good building. This building can easily install a small up to 5 kilowatts PV system on his roof, and it can produce all the energy needed for the building. And one word about the cost. Sorry for this Greek slide. The total cost for renovations were about, as I told you, 52,000 euros, which means less than $60,000. $375 per square meter is the total amount, which is a very good amount for the Greek market. Now, the pros and cons in total. As I told you, plaster is the airtight layer, and this is a very big advantage. which reduces the costs. The other thing is that we have a very small average temperature difference between inside and outside because we are in a happy climate zone, like something like California in US. This gives us advantage in order to minimize thermal breaches, especially in balconies. Also, the suspended floors, which are common in many buildings, especially in Athens, and the parapets add more insulation and are raising the cost. But as I told you, the detailed planning can find the cost-effective method. And another big problem in multifamily renovation in Greece is the ownership in multifamily houses. We have almost one owner for each apartment, and this makes the common decision for starting a renovation project very, very difficult. The results of deep renovated buildings also in Greece includes these main three categories: very low heating and cooling demand, which can easily be covered by renewable energy sources on the building or close to the building; a perfect indoor air quality, something which is totally new in Greece, something that gives passive houses the biggest advantage comparing them with other buildings; and of course, economy, especially now where everybody is one step before energy poverty. The passive house owners feel more independent than all other consumers, having a building worth living and spend time in it, having a healthy building. One word about prefab renovation concepts in Greece. This is a discussion that just started in our country. We think that there is an option for prefab renovation, especially in schools, as you see, because they have a very common typology all over the country, and all co-housing immigrant buildings, as you see in the two pictures on the bottom of the slide. We will attempt to renovate such a building in Athens next year, the right one, the right bottom one, and we will have more things to say after that. This is a very interesting project that we have in front of us for the next 2 years. So, as a conclusions, what are we aiming through the outPHit project? Imagine you want to buy a smartphone and there is no single retailer who can tell you about its features, what it will cost, when it can be delivered, or if it has any kind of warranty. A far more complicated version of this is where people typically find themselves when they wish to renovate their buildings. We believe that this is not only unacceptable, it is one of the biggest hindrances on the path to reducing emissions from the building stock. outPHit makes deep retrofits faster, cheaper, and more reliable by bringing all the pieces together to facilitate rapid, deep retrofitting solutions. I'm here for any further questions. Thank you for your attention.
Hello, everybody. My name is Etienne Vekemans from Paris. I'm working from Propassif in France, and we are one of the 7 European countries taking part in the outPHit project. As you may know, outPHit project is dedicated to the development of cheaper, faster, and more efficient retrofits made with prefabricated modules. Well, the idea of the prefabricated modules is quite simple on the paper. The idea is to use prefabricated modules assembled in factories outside the construction site in order to renew the facade, the roof, and probably also the ground floor in order to reach outPHit levels for the whole building. Which may be either in classic outPHit, plus outPHit, or as well premium outPHit. The interest of using prefabricated modules is that you reduce the time spent on site, and you reduce the disturbances for the inhabitants of the project, as well as you enhance the precision of the work done in workshops on the modules. Well, let me introduce you the subject of this presentation, which is the Colbert project. Actually, it's too big a project to be renovated and analyzed through the 3 years time frame of outPHit. So it's not a case studies within outPHit, but it's an observer project. So it's observer project number 8. The original building was built in the early 70s from the social landlord called Le Girep in the Parisian region. It's actually built in Colombes, in the outskirts of Paris, and it was nearly 50 years after it was built in 2013 when the project started. It was in actually real need for renovation. Well, what was actually the Colbert project? It's not just one building; it's 3 buildings called A, B, and C, which is very original. But anyway, building B is about 2,500 square meter. Building B is 1,500 square meter, and building C is nearly 2,000 square meter of treated floor area, which means as a whole, the Colbert project is about 6,000 square meter, which made it a quite big project within outPHit. In its original status, it was also it has an energy performance index of D, which is quite bad, and moreover, it used a lot of gas. So there was really many reasons to renovate the project, and now you will see the project renovated. It was actually the project itself was renovated thanks to EU subvention as well as the region subvention, which made it happen. The project actually counted 70 dwellings, ranging from 2 rooms to 6-room apartments, and it used the prefabricated modules from technical called panel block, which I will present afterwards, which brought the over insulation of the facade, the change of the windows, the treatment of the thermal bridges, the treatment of the air tightness, and the optimization of the compactness of the thermal envelope. And last but not least, which brought also a range of high-performance technical systems, ranging from the ventilation with heat recovery, as well as pellet heat systems. Let's have a look now at the experts involved on the project. It was the landlord, Le Girep. The architect which made the renovation possible is called Langtwit. The general contractor is FH Construction. The engineering bureau is Indigo. The wood structure enterprise is Ecologia. And the steering company is called Biotop. And the specialist for the facade is as ACTR. Let's have a look now at the project from the air. You see on the left side the building A, the bigger one. which is on Colbert Street. The building B is also on the same Colbert Street. And the building C is on Rue des Codotis, which is nearby. You may notice that the original construction was very cubic. It was quite typical of the architecture of the early 70s, with reinforced concrete and flat facade, which could make them easier to renovate than other facades. By the time, it was a symbol of very high modernity, but 50 years afterwards, now it's a symbol for the ugliness of the banlieues in the Parisian region. So this was also the reason for the change of the facade and to give the building a nicer look than the one it had. Now this is actually before and after of building B. You remember it's not the big one; it's rather the smaller one. The prefabricated module was a possibility to reshape the architectural impact of the building. Well, how did it work? Here you've got the layout of the prefabricated modules on the facade of building C. It's actually the street facade where you see the assembly of panel block as well as of just timber frame modules. The absolute need for this layout is that the work in the factories bring no surprise when the prefabricated modules are brought on site. Let's have a look now at those panel block modules constructed by Techniwood. You see on the left-hand side the panel block modules brought on a simple concrete wall, and on the right-hand side you see the integration of the windows, of the new windows within a panel block module. You may also see that the panel block modules is built out of 9 ply of very standard elements, which are planks of wood. You see here the panel block modules before leaving the factory. You see the planks which made actually the modules himself, and you see also the green the green sleeves, which are the isolation. So the interest of those panel block modules is that the construction of them can be fully automated. On the left part of the slide, you see the coding of the PHP of such a panel block module, which bring at the end U value from 0.1 to 1, which made it absolutely completely fit for the EnerFit renovation. Here you see what hasn't been renovated with panel block modules, but with sound ethics. On the left-hand side, you see a cut of the wall, the renovated wall. And on the right-hand side, you see the over-installation of the frame, which is a typical way of construction in Passivhaus modus. Here you see the C plus D process for justifying the C plus D certification of the building, which is mandatory. And now you see the rooftop of the 3 buildings with the heat recovery ventilation. So typically, the blue pipes are the pipes with fresh air, which you see start from the roof and go through the prefabricated modules to the apartments. And the red pipes of ventilation is actually exhaust air. So you see the exhaust air come through the old chimneys of the building to the top, where they deliver their energy to the fresh air. Now we come to the end of this presentation. We could make a partial sum up about costs and CO2 emission of the renovation. Well, the cost, you see, it's roughly €600 per square meter, which is half or a third of the cost of a new build, but quite expensive for renovation. But it's a renovation to a new build standard. So, well, on the other side, we see the energy carbon saved per year. It's about 18 cubic meter of gas, which is roughly 200 tons of CO2 per year for the whole 3 buildings, for the 6,000 square meter. And the carbon saved on non-deconstructing the building is about 700 cubic meter of concrete, which is roughly 700 tons of CO2. Well, you see that on a calculation on 100 years, the project is interesting for a ton of CO2 of €180. What is also interesting to notice is that on 50 years, the renovation will save about 10,000 tons of CO2. Well, what could have done Energies better for the project? There's a whole range of work package which could have brought interesting results for this project. Starting from task 2.7, which is the design stage approval, which hasn't been done actually because of the project that before, but could have helped the landlord in taking a decision. Also, the task 2.1 about summer overheating stress test could have been interesting for the landlord. The decision support on task 4.2 and its PV econ would have been interesting as well. The next part of the green energy assessment tool would have been interesting to know before starting the project what would have been saved. Also, the task 5.4 about cost of documentation would have been a help for the project. And last but not least, the monitoring, which is done within the outPHit project, could have helped the project Colbert. Well, this is the end of my presentation. I'll be available for any question you have, and I thank you much for your attention.
Hello, my name is Nuria Diaz. I'm architect and Passivhaus certifier from Band Arquitectura in Spain. In this short presentation, I would like to show you one of our case studies from outPHit. The project is a social housing retrofit in the city of Teruel. You can see in this slide pictures of the building before and after the retrofit. It is a multi-story social housing for rent with 10 apartments. The owner is the public government of Aragon, and the construction works are going to finish this month of June. New tenants will occupy the building in the next months, and we expect to start with the post-monitoring works next January. It is a very interesting case study for us because this typology is quite common in Spain, and we can find thousands of similar buildings in every city. Here you can see the map of Spain, and you also can see where Teruel is located. Although the city is located in a warm temperate climate country, it has quite cold winters due to the altitude of the region. Teruel is almost 1,000 meters above the sea level. The lowest temperatures in Spain are measured every winter in a place close to the city of Teruel. First of all, I would like to show you some results of our pre-monitoring works, which can help us understand the poor conditions of the original building. It is also an example not only of this building, but of all buildings of the same typology. These infrared thermographies show very low temperatures in the inner surfaces in the thermal envelope. We can find 8.4 degrees in the connection between wall and ground floor, and 9.7 degrees in the corner. Mold is even visible in several areas of the wall, especially in the corners. Here, two more pictures showing the temperatures on the north facade and below the inner temperature on the frame. Comfort is of course not achieved in the interior of the building. Here we can see two graphics, one with the temperature inside and one below with the temperature outside. You can see that inside air temperatures are always below 18 degrees the whole day, reaching a minimum of 11 or 12 in some moment in the night. And if we compare with the outside temperatures, we can see that it's not particularly cold. 15 degrees are achieved in the warmer hours of the day. So that means that the envelope of the building is quite bad. You have to understand that using the heating system is a cost that many families cannot afford. This is a social housing building for low-income families. In the context of outPHit, we made the PHPP calculations of the original situation of the building and the retrofit. You can see here the results. The main goal of the project is to achieve the Energiefit standard. So in this case, we had to work using the component methodology, and we could improve the heating demand from 400 to 42 kilowatts hours per square meter and year. As you can see here in this graphic. Now I would like to show you some pictures of the construction works. First, the external insulation of the ventilated facade with 140 millimeter of mineral wool. You can see here the window installation detail using, of course, a roller shutter for sun protection in summer. As you can see here in the picture, the connection between window and insulation are not already done. There is still a missing piece of insulation for this connection. This is this kind of installation of the window towards the interior of the wall is quite common. It's a quite common solution in Spain, used to create shadow and reduce solar gains in summer, which is normally more convenient than reducing more the installation thermal breach in the winter. In any case, the frame has to be covered with this insulation. One of the most characteristic details of this typology are balconies. We can see here the construction detail and also a pictures. So is how we minimize the impact of the thermal breach. The original building had no ventilation system at all. Now, new ventilation units have been placed in the suspended ceiling in the bathroom of its flat, and all rooms in the building are ventilated to ensure air quality. The main characteristic of this building in relation to the airtightness is that we worked this airtightness per flat and not including the whole building envelope. The reason is these common areas are opened to the basement and the cellar, and we found some difficulties to improve the airtightness of this area. The lower is made of concrete for the floor and ceiling. We always try to use the existing concrete, plaster to cover masonry walls, blower proof for the connections, and tapes for window installation. And what are our challenges now with outPHit in Spain? What we discovered is that prefabrication approaches are not common here. These kind of solutions are not available in the market and also are quite expensive solutions. outPHit brings us the opportunity to demonstrate how important it is to improve processes in retrofit works to meet our goal of renovating all our buildings to Energiefit, or at least to a high efficiency standard. And this is just the beginning. More information of the project will be available soon in the web page of outPHit. Thank you very much for attending. Comments and questions now on the chat, please.
Hello, everybody. My name is Fabian Ochs. I'm happy to present today the work we've done together with my colleague, Vekemans, on the PV Econ tool, which was done in the framework of the Age 2020 project outPHit. The motivation of this work is that increasingly it's requested to integrate PV, heat pumps, and energy storage in buildings. We see here an example of a single-family house with a heat pump and maybe some storage options, domestic hot water store or a space heating buffer, or maybe using also the thermal mass of the building. And you might integrate PV, or should, and maybe also additional electric storage. As an example, you see on the right-hand side the electric energy balance. The green line is the total electricity in daily energy. And we see the contribution from the heater, the heat pump in this case, the domestic hot water preparation, appliance, and also some auxiliary energies. The total electricity without any PV is equal to the grid electricity, the electricity purchased from the electricity provider. In this example, we have a small domestic hot water storage. Now, if you integrate photovoltaics and we keep the storage like before, then the picture changes quite significantly. Now the total electricity is still the same, it's the blue line, but the purchased electricity is slightly decreasing, in particular in summer, there's almost no. We have instead PV excess electricity, coming from the rather large PV system of 5 kilowatt peak with high contributions in summer and obviously lower contributions in winter. This is done for Central European climate, as an example, Innsbruck in Austria. If you integrate some small electric storage, the pictures only slightly changes. We see, in particular in summer, I switch back, we get rid of some of the electricity small peaks, positive values in summer. And there's some influence on the excess PV, almost nothing happens in winter. Only if we integrate large battery, so because we already have a balance on a daily basis. If you integrate large batteries, we see some more changes, in particular in the transition season, but still, of course, we have electricity purchase in winter, and we still have PV excess in summer. Still, the question is, what is the optimal size of the PV system from an economic point of view? It should be obviously as large as possible from the environmental point of view. Should we integrate storage? Which type of storage, thermal, electric, and what is the optimal sizing of the storage from the economic point of view? And that will depend on fuel and electricity prices, on initial costs, and also, of course, on subsidies, taxes, and so on. So the goal of this PV econ tool is a tool with a spreadsheet-based approach, which can be added to PHPP for the economic evaluation of this PV system in the building, depending on the building energy demand, its HVAC system, its PV system, and PV size, and also the storage options and storage sizes. The structure of the tool is such that we can calculate first the part of PV electricity that is directly consumed in the building, the so-called PV own consumption, and the grid electricity, and we need this on a monthly basis. And for that, we use the inputs from PHPP, the heating and electric loads, the PV yield, and the HVAC options, heat pump, and so on, and also the economic parameters. Also, of course, climate and all other parameters. In the PV econ tool, we calculate based on the storage option and storage size, the monthly electricity demand and the PV self-consumption. And we give as an output monthly electricity consumption of the building, including heat pump, appliances, and auxiliaries. We determine the load and supply cover factors, the monthly CO2 emissions, or alternatively, the non-renewable primary energy. And this is then the basis for the economic evaluation. We can consider the following HVAC types, all types of heat pumps, also in the heat pump compact units, direct electric heating systems, also combined with heat pumps, for example, heat pump for space heating, electric boiler for domestic water, and also other maybe less relevant systems for this PV on consumption discussion, but all are included: district heating, oil or gas boilers, and biomass heating. Also, we can include solar thermal in the calculation. The PV econ tool allows for 4 storage options. We can consider no dedicated storage, so just the standard thermal mass of the building without a specific activation, and maybe a domestic water storage, which is not specifically used. Then we can use the small storage such that we increase the PV own consumption by means of operating the heat pump or the heating rod mainly during daytime. Then we can integrate battery systems or combination of both. In this case, the domestic water storage or small means that we have a domestic water storage. For a single family house, it is, for example, 150 liter, and it's charged only during daytime, while electric storage, a small electric storage means a typical size of something like 1 kilowatt hour per kilowatt peak, which is just enough to store the maximum night load in summer, which is then the type of battery storage. And we can here see an example of results. On the upper left, we see the electric balance of the heat pump, which has contributions in winter of space heating and domestic water. Because in this case, it's an air source heat pump. The electric consumption is significantly higher in winter than in summer with the high source temperatures. So we have a quite strong seasonal behavior of the heat pump. That is added to, on the lower left, the electricity demand on monthly basis for appliances and for auxiliaries. That gives the total electric demand curve. And then if you combine this with a PV system here, a fairly large PV system with a lot of PV excess electricity, still we see significant electric demand from the grid, also on a monthly basis in winter. And this is because the PV own consumption is relatively small because of the day-night problem can be covered, but of course we have low PV availability and high demand in winter. Therefore, the contribution can only be significant in the summer months. The remaining curve, the gray curve, is the electricity bought from the grid, and this is also displayed in the diagram. Additional information is then in this tool the load cover factor and supply cover factor, and the annual CO2 emissions, which is in this case also strongly seasonal, also the CO2 emissions. In addition to the PV availability in summer and the higher electricity demand in winter, we have also the effect, considering as an example the Austrian energy mix, that we have large contributions of hydro in summer, and also the PV and other renewables in the grid will contribute mainly in summer. That would be a little bit different for wind, which has also higher contributions in winter, but that is almost not existent in Austria. Therefore, we have this seasonal behavior. The economic tool is part of ongoing work. We will, based on the thermal and electric balance and using investment costs, including PV and batteries, and maybe also for increased electric or thermal storage. We will calculate then the sell and buy electricity prices. With the sell and buy electricity prices and with the subsidies, the electricity costs per month and per year. Considering the lifetime of the components, interest rates, and maintenance, we can calculate the life cycle costs for each variant and optimize for that. This is part of ongoing work. To sum up, we have the PV Econ tool as a PHPP add-on, at least a future PHPP add-on for the economic evaluation of PV systems and buildings. We can calculate the building electricity demand on a monthly basis and the PV own consumption as the basis for the economic calculations. And in future work, we should consider also non-residential buildings. We will work on enhanced storage options, also include car charging, which is already simulated but not yet included, and maybe also relevant for cooling dominated climates, of course, HVAC and cooling. With this, I want to thank you. As mentioned at the beginning, the project is funded by the European Commission within the H2020 Research and Innovation Program, and I'm happy to receive your questions.
So hello, it seems Fabian has finished his presentation on the PH Econ. Very interesting still for me, even though I've seen it a lot of times in the meantime. Anyways, we have some minutes left for questions, 5 or 6, if I understand correctly. I have checked the chat all the time, and I think that lots of questions have been answered by Stefan, Nuria, or Etienne in parallel. Is there any more questions that we could answer?
Maybe I can answer to one question of Monte Paulsen, which I haven't answered completely, I believe. Do I?
Go on.
So the main question was, he wonders how did people say yes to the outFIT project? So how did the owners of the existing buildings said yes to the outFIT projects? Well, the main reasons were mainly the energy bills or the quality of life. But I believe that in the 2 of the 3 cases in Greece, the people came to us because they were well informed, very well informed. So they came to us and they said, I want to have a passive house. So I believe that the main reason for that is to inform well the people. Then if they know what passive house is, then they choose it all the time. In the third example, in the multifamily building, this was a very difficult exercise for us because we have done a discussion with these 12 owners for more than 6 months in order to convince them to follow the project. We convinced 9 of them, but we didn't convince 3 of them. And because of this situation, the project couldn't go on. And that's why we decided to do only one apartment renovation in order to show to the rest what have they lost, let's say. So this is also an important example, the last one, which shows exactly what Monte says, that even not a technical problem, but a political problem or a business problem is also important to overcome in order to make a renovation in a multifamily house.
If I understand correctly, Stefan, you're with the one family of the single family house. They went down from heating bills of 5,000 euros down to 500.
Something like that.
In the worst winter you've ever had in Greece.
Yes.
Since Athens was conquered or whatever that was.
Mm-hmm.
So that was really amazing. I mean, just being there in this house and talking to the owners was encouraging that we're doing the right stuff, if you want to hear my opinion. So it was really worth it. I'm looking forward for the interviews you're doing with them. So I have another question here, which Chris Petit asked, if the pH Econ tool is also taking into account embodied carbon into the analysis. Fabian said might be included. I could add here, we have this pH, this embodied energy evaluation tool. We have also set up something in the outPHit project to evaluate embodied carbon in a passive house. So you could also enter there the embodied carbon in a PV system, right? That could also be possible there, but I mean, we could surely think about anything in this pH Econ tool. Fabian.
Yes, hi everybody. Sure. So currently we focused on the energetic evaluation, and the economic part will be then added on. And I think to integrate the carbon footprint of the PV is more a simple exercise. So that would be doable, of course. But I don't think it will be a game changer in case of photovoltaics.
Yeah. Thank you. Is there any more questions here in the chat? I can't see them. So I guess most of or all the questions has been answered actually. And at least here in Darmstadt on my computer, time is running out. So I guess we all say goodbye to you over there in the US. And thank you for listening. Thank you for paying attention. And yeah, hope to see you soon. So goodbye, everyone.
Thank you. Goodbye.
Bye-bye.
Bye.